in this portion, now that you know how to use a calculator, now we're going to start adding context to those calculations we're doing. So it's not just going to be me saying, hey, find the proportion with z bigger than this. Now we're going to add some context to it, and I actually think the context makes it easier to understand. Okay, so it's not just numbers you're looking at. Now you know what you're actually discussing. One of the best pieces of advice I can give is this right here. That's kind of your little flow chart to how everything these next couple days are going to flow. Okay, so there's three kind of phases that we're talking about that we need to be able to go back and forth between. Giving you just looking at the observation itself, the data itself, finding the z-score, or finding a percent or percentile, proportion, whatever language they're using. Okay, so you need to get comfortable today how to go back and forth between those different phases, okay, those different things. Now, yesterday, I showed you how to use these calculator commands, all right? So if I have a z-score and I want a percent out of that, I can use normal CDF. If I'm starting with a percent and I need the z-score, I need to use inverse norm. So again, this is going to show you exactly what you need to do for every single problem that we're going to have today and on Monday. They're two of almost kind of the same day. Um, so let's just kind of dive in, and then you'll kind of get a sense for how that diagram works. So, on the driving range, Tiger Wood practices his swing with a particular club by hitting many, many balls. When Tiger hits the driver, the distance the ball travels follows a normal distribution with mean 304 yards, standard deviation 8 yards. What percent of Tiger's drives travel between 305 and 325 yards? All right. So the first thing that I pick up on, now this is going to be common throughout this entire chapter, but later it will be important to pick up on key language. The key thing that I notice is that they're telling me this is a normal distribution, okay? Because when we get into chapters 5 and 6, it's going to be very important that that is a big indicator that we're doing this process. Of course, right now, everything is this process. But again, I want you to get used to identifying that key language, okay? So the thing that sticks out to me the most is that this is a normal distribution. If we kind of look at what my expectations are or what their expectations are for the test, if you're working with a particular style distribution, you should label that distribution, okay? So what that means is even though it seems relatively obvious because they just kind of spoon feed it to you, you do want to note that this distribution is normal, centered at 304, standard deviation of 8. I do require you to show me that label because they are going to need you to discuss that label, okay? So whenever you're dealing with these word problems on a free response question, that is the first thing you should do, okay? Just label, hey, I know what I'm talking about. I know what this distribution is. Now, this is where our flow chart comes in handy. So we're looking for, or we were given these observations, right? So we have these observations, and they're asking for a percent. What percent of observations fall between those two? All right, so if I'm starting with observations and I'm trying to end with percent, I have kind of a stepping stone I need to get to first. What's in between these two? Where do I always stop in the middle? Z-score, okay? So literally always to go between an observation and a percent, you always have that middle ground you have to hit, right? This shows us that we need to find the Z-score, and again, good news, you have a formula for that, don't you? You know how to find a Z-score. Now, in this case, we have two observations, we're in between, so how many Z-scores do we need to find in this case? 2 Z-scores. All right. So I'm going to find the Z-score of 305. And again, according to the flowchart, just to remind you, the Z-score is that observation minus the mean divided by the standard deviation. But again, we established we need to do that twice. We need to do that for both of our observations. And I need a calculator too for this. All right, so I have my z-scores, and now again, let's look to see where that flow chart is sending us now. So I'm setting a z-score. I want the percent between there. What is my flow chart telling me to do? Normal CDF. Okay, so that's why I said this is going to be so important. If you can remember this, it literally has everything you need for this entire second section, almost. Okay, now again, the reason that I like to have you label it just like this and show this work is because now I also want you to show me what you're typing into the calculator. Okay, now that's why this is important, because if you don't show this, the work you say with that calculator syntax means nothing to the test graders. But if you have established that, now they know what you mean. So here, I would actually show me, hey, I'm taking normal CDF, right? And I'm going from 0.125 up to 2.625. Okay, I want you to show me what you're typing into the calculator, because then if something goes wrong, at least I can see why. At least I can see what you were trying to type in. Okay, so from here, actually another good thing to remember, where is normal CDF in the calculator? Where do I go? Distribution, yeah, second vars. Normal CDF. And again, this is a version that we like because it's bounded on both sides, right? It's bounded below and it's bounded above. And again, some of you, if your calculator isn't as fancy as mine, you may just have to type this in your home screen. Some of yours will just pop this normal CDF thing up, and you'll have to just type in lower, comma, upper, and it would give it to you. But the answer is that. And again, common practice, how many decimals did I say we usually show when it comes to probability? What's common? 4 decimals, yeah. So 0.4459. And again, I put the normal curve over there because you can actually show on the normal curve what you're doing. We're going from 305 up to 325. And that does look realistic, right? That 44.59%, that looks realistic compared to what I just shaded. If you got something completely different, then maybe that's something to question the math that you just did. If you notice that this is obscenely different than this, okay? Now, this is an extension. This is an extension of the same problem. So once you've established this once, you don't have to do that again, okay? So this is a continuation of the same problem. So because I've already told you what distribution I'm working with, you don't have to tell me that again, okay? You've already mentioned it in part A. I don't need that same thing in part B. Now, part B says, what is the 20th percentile of his drives? So here, basically, what is the observation at the 20th percentile, right? How far is that ball going to go? Well, this time, would you agree? I'm starting at percentile. I want to know how far is it going, right? Now, again, same thing. Where's that stepping stone? Where do I need to go first, always? You always have to stop at z-score, right? You cannot go straight from a percent to an observation. You always have to hit that middle ground, that z-score first. Now, also remember, where on the calculator do we go? If I'm starting with a percent and I want it to kick out a z-score for me, where am I going? That inverse norm, because it's the opposite of what we just did, right? Normal CDF, put in a z-score, pop out a proportion. Inverse norm is the opposite. Put in a proportion, pops you out a z-score, okay? And again, same thing like I said above, I do want you to show me what you're typing into the calculator. I want to see what you're doing, so if you end up with the wrong answer, at least I know where it came from, and they will know where it came from. So, I'm going to type in the calculator inverse norm, 0.2, because that's 20%. And then we're going to see what the calculator gives us. Isn't inverse norm in the same place as the other one, right? The normal CDF command. So if I know where normal CDF is, I know where inverse norm is. So under distribution, go to inverse norm. I know yours looks a little bit different. You don't have these same options as I do. You're only going to worry about typing in 0.2. Or if you have to type it in yourself, again, you're not going to have any of that on your calculator. And so again, something that I encourage kids to do is always going to keep in mind, what did you just find? What is this number? It's a z-score, yes. So again, I always encourage kids also write down what you just found, because again, the longer these problems get, it gets very easy to lose what you're doing, like lose track of where you are in the process. So I always recommend, yes, so you just found that this equals negative 0.84. And I always encourage kids to write down, all right, that's my z-score, okay? So we just found a z-score. And again, we're still trying to progress to find that observation. How far is that golf ball going to go that's at the 20th percentile? Well, going back and forth between these two is actually exactly the same thing. Both ways, can't we use the formula? Right? Either direction we're headed, we're going to use that formula. What's different is how we use it, though. This time I know the z-score, and what I'm missing is the observation, right? So depending on what direction you're heading, it just rotates where you're putting the information into the formula. But you always use the formula. Centered at 304 divided by 8. Okay, and now let's talk algebraically. How do we get x by itself? 2 steps. Multiply by 8 and add 304. Now, let me show you a trick, okay? I like to keep things as exact as possible. So let me show you how you can do that. Because isn't negative 0.84, isn't that rounded? That's a rounded value. But if I don't do anything else first, if I just say, hey, I want to multiply that by 8, now in my calculator at least, it's still an exact value, right? So again, try your best to keep these as exact as possible as we're working. If I say, hey, I'm just going to multiply that by 8 and now add 304, now my answer isn't rounded to the very end. It kept that exact answer all the way through until here. And now isn't this our final answer? How far it would have gone? And again, there's no firm rules for decimals, so I would say in this case, just put 1 or 2 decimals for the observation. So we could call this 297.27, and I think, was it yards we were talking about? I can't remember. Yeah. So 297.27 yards. All right. All right, so let's up our game a little bit. This one is a little bit more challenging, but again, I like it because it encompasses all the ideas that we are working through here. So, an important measure of performance of a locomotive is its adhesion, which is the locomotive's pulling force as a multiple of its weight. The adhesion of one 4,400 horsepower diesel locomotive varies in actual use according to a normal distribution, with mean 0.37, standard deviation 0.04. Again, I know right now every single problem is going to be a normal distribution, but do get into the habit that is a key word to focus on, okay? That is what tells us we can do this process, okay? Because we know we're dealing with a normal curve here. So for a certain small train's daily route, the locomotive needs to have an adhesion of at least 0.3 for the train to arrive at its destination on time. At what proportion of days will this happen? All right, so this point 3 that they gave us, isn't that a particular observation we're talking about? And we want to know what proportion of days will this happen on, right? What proportion of days do we need at least an adhesion of 0.3? All right, so again, let's reference what we're doing. So we're starting with an observation. We want a proportion. What proportion of days will this happen for? Where's that first stepping stone? Where do we need to get to first? Z-score, right? And again, that's why I hound this diagram so much because, again, if you know the diagram, you're not going to mess up what's going on. The other thing to remember is, don't I also always want to start by establishing the distribution we're talking about? Is normal, centered at 0.37, standard deviation of 0.04. Okay, and then you just told me that to go from an observation to a proportion, we need to stop at that z-score first. Okay, so I'm going to z-score this. Z equals the observation we're talking about, that we're wondering about, is 0.3. Its mean is 0.37. Standard deviation, 0.04. 0.3 minus 0.37 divided by 0.04. So we're getting a z-score of negative 1.75. All right, again, we're at z-score. Now let's check to see, headed this direction, got my z-score. Now where do I need to put that z-score to get a proportion out of it? Normal CDF, yeah. And again, I want you to write out what you're typing in the calculator. Again, it'll help me know what you're doing. It'll help them know what you're doing. So normal CDF. Now, one thing to consider is when using normal CDF, we need to know the bounds, right? Lower and upper. So if we're saying we want at least this, isn't this the lowest we can accept and then we need greater than it? Isn't that what at least means? Right? So in this case, we're going to be starting at that negative 1.75 and then just heading on up, right? Now, remember, the normal curve technically goes on forever, doesn't it? So what do we do because our calculator doesn't recognize infinity? What do we put as our upper bound since we can't type in infinity? Yeah, just a big number, right? I usually settle for 1,000. Again, even 100 would honestly do, and obviously anything bigger than that will also do. Okay. Then in the calculator, clear that out. Distribution, normal CDF. Put in 10. I'm pretty sure that should also do the trick, actually. Is it the same? Yeah. All right. And we go for how many decimals? 4. So 0.9599. So this trade looks like it's going to be in pretty good shape, right? 95, 96% of the time, it's going to be there on time, right? All right. An adhesion greater than 0.5 for the locomotive will result in a problem as well because the train will arrive too early at a switch point along the route. What proportion of days will this happen? So, what proportion of days will it actually end up getting there too early? All right, now again, part A, we already established what this distribution is. So do I need to repeat this? Do I have to put that in part B now? Nope. It's already stated, right? And nothing's changed, so we're good to go. All that's changing is we're looking at a new observation, right? Now we're curious about this 0.5. How often will that happen? So, again, same thing. If you ever need to reference this, we're starting with an observation. They're asking us about the percentage. So where's that first stepping stone? What do we have to do first? Always z-score. Always. So here, this time the observation is 0.5 minus the mean, which was 0.37, divided by the standard deviation. And again, the question is, how often will this happen? How often will it be there too early? Well, isn't it if it's bigger than this, it'll get there too early? So when I'm setting up my bounds for normal CDF, if it's bigger than this that we're looking for, isn't this going to be the lower bound and we're heading upward from there? Does that make sense to everybody? Yep, so we're starting here, 3.25, and we're heading on up. So again, just to some big number. And I think you guys have the point by now, so I'm just going to go into my calculator. I'm not going to project it on the board this time because I think you guys by this point know where you're headed, right? Now, if you notice, isn't your calculator giving you a little bit something weird? I have 5.77, then this e to the negative 4 at the end of it. Does anybody remember, what does this mean? There we go. Isn't this scientific notation, technically? So isn't this saying, hey, move the decimal 4 times to the left? So really here, what we're talking about is 0.000577, right? We're talking about a very small proportion of times it'll get there too early, which is probably a good thing. So if it gets to the switch point too early, aren't you talking about like possibly crashing into a different train? Wouldn't that be really bad? So it's probably a good thing that this is obscenely small because we don't want this happening. All right. Any questions so far on what we've done? Is this okay? Is this better than yesterday? I think it's a little bit more clear now. Yeah. All right. So let's talk about some more interesting circumstances. Okay. So the locomotive's manufacturer is considering 2 changes that could reduce the percent of times that the train arrives late. One option is to increase the mean adhesion of the locomotive. The other possibility is to decrease the variability in adhesion from trip to trip. That is to reduce the standard deviation. So we have 2 options because they obviously want to reduce the number of late trains because weren't 5% of the trains late. So they want to try to adjust this, okay, make that smaller. So what they're saying here is, let's say that the standard deviation remains at 0.04. Let's say that that's fixed, okay? What value do we need to change the mean to so it arrives less than 2% of the time late? So we're trying to reduce from 5% down to 2%, okay? So we're starting with a percentage this time, aren't we? We're starting with a percentage, and we're trying to figure out how do we have to adjust our observations, adjust our mean to make that happen. So this time, again, that stepping stone is still the z-score, but how do we get there? How can I put in a percentage and get a z-score back? What program does that? Inverse norm, yes. So we want it to be late less than 2% of the time, okay? So in the calculator, again, less than 2% of the time, if we're looking at the normal distribution, we want to minimize this to 2%, okay? And again, the nice thing here is, isn't this already the percentile? We don't have to flip anything to make this happen. So we need to take this and inverse norm that point or that 2%. I can't just type a 2 in though. What is 2% as a decimal? 0.02, yeah. because again, less adhesion is representing it being late, so that's why we're focusing down here, okay? We want that adhesion to be less than it only 2% of the time, okay? Because that represents being late. So, and again, what did we just find here by doing this? We just found the z-score, didn't we? Yeah. So, negative 2.05 is our z-score, okay? So we inverse normed 0.02, which gave us a z-score negative 2.05. And again, just to help you keep track of your work, to make sure you understand where in this process you are, I do encourage you to write down that you did just find a z-score. Okay? Now, again, how do we go from a z-score to an observation? Plug it in. There's a formula for that, right? Now, here's the interesting part. Okay? So, isn't the mean what's fluid here? Aren't we trying to find the mean? What observation is our focus still? What represents being too late? What adhesion? It was at the beginning of the problem. What adhesion represents being too late? That's too early. 0.3. 0.3 is the observation we're still focusing on, right? Because 0.3 represents being too late, what we want to know is how can we adjust the mean to make this happen, right? We're trying to change the mean of this process to drop this down to that 2%. So this time we've actually reversed what we're looking for here. We're looking for the mean, not the observation. We're still focusing on 0.3 because that represents being too late. Again, some algebra for you. What's the first thing we would do algebraically? Times this over, right? When I times that over, I'm going to get... So I'm going to multiply this by 0.04. All right. All right, now I want us to think about this. So right now, the formula is 0.3. That would equal 0.3 minus the mean, right? So I'm trying to think how I can do this as exact as possible, continuing it along my calculator. Wouldn't you agree that if I add this over here, I would have mu minus this equals that. So couldn't I realistically add this over? Isn't that what I need to do? Right? Add over that 0.08. So really what I need is 0.3 plus my answer. But that answer, to make it positive, I'm going to multiply by 0.1 because I need it adding over to the other side. So isn't that what that would look like? To take 0.3 and add 0.08 over to it? So this adhesion, if we made this our mean adhesion, we would drop our late trains down to only 2% of the time with that adjustment. Is everybody with me still? Yeah? All right. Oh, because I wanted to add this over, but it's negative. So I had to multiply by -1. So I was adding it to the other side. That's the only reason I did that. No. All right. Well, we don't even have that much more, really. All right. All right. Shh. Now, part C, we're switching it up. Now they're saying, what if we leave the mean at that 0.37, right? Let's leave the mean alone. What if we can find a way to decrease that standard deviation? How much would we have to change that to get the same result? Being late less than 2% of the time, okay? Now the good news is we've already done a good portion of this work, right? So we're trying to find a new standard deviation, okay? So we're still working with the same observation of 0.3. We're just trying to find what standard deviation will make that happen. We still want this at 2% of the time, okay? So to make that happen, that 2% of the time, don't we still have to stop at the z-score? But didn't we find that last time? That hasn't changed, has it? The 2% we used before is still going to be the 2% we need now. What was the z-score we found from that? Negative 2.05. So because I'm dealing with the same percentage, my goal is that same percentage, that z-score hasn't changed, okay? So here, that z-score that I got from that inverse norm is the same one we're still going to use, okay? We still need that same z-score. Now the difference in this process, though, is now we're saying we're trying to decrease the standard deviation, okay? We know the z-score, right? We're still looking at 0.3 because that represents being late. They say this time we're keeping the mean the same. We want a new standard deviation, okay? We can combine the tops together, right? Wouldn't that be relatively easy? Negative 2.05 equals negative 0.07 divided by sigma. Now again, talking algebraically, how can I figure out what this is now? There we go. So I multiply this up, divide this down, right? If I do that, won't that give me my new standard deviation? All right. All right, so here I'm going to redo this just because I want that exact value. Because didn't we say to take negative 0.07 and divide it by that, and that'll give us the standard deviation? So if I dropped my standard deviation down to this, now the train's only going to be late about 2% of the time. All right. Now that we have both of those values, let's talk about which of these methods is going to be better. Okay? Which method is going to help us more? So, we got this to be, what, 0.034, I think? Yeah. Which one is preferable? To make the mean greater or decrease the standard deviation? Which one do we think is going to be a better option for us? Let me put it this way. So, it talked about if the adhesion is too big, doesn't that mean the train is too early? And we're talking about the consequences of having the train too early. Well, in part C, didn't we raise the mean? If we raise the mean, wouldn't that make this slightly more likely to happen? If we push the mean closer to this, isn't it likely or a little bit more likely to happen? So a consequence of shifting the mean up, we're risking those trains being too early to that switch point and colliding, aren't we? Wouldn't that be a really bad option? Do we want those trains colliding? No. If we decrease the standard deviation, Actually, the end result of that is both end up decreasing. Less likely to be late and it's less likely to be early. So ultimately, which choice is going to be better? C or D? D. D is better because again, C has some natural consequences to it. It will make trains more likely to be early, and again, that's bad. So we'd much more likely decrease the standard deviation because it decreases both things, or the likelihood of both things from happening. All right. So let's do one multiple choice, and then I'll give you guys some work time. So the average yearly snowfall in Chillyville is normally distributed with a mean of 55 inches. If the snowfall in Chillyville exceeds 60 inches in 15% of years, what is the standard deviation? All right, again, the key thing that I see right away is they mentioned that this is normally distributed. If you know that it's normally distributed, that tells you that we're using the process from today, okay? That is our key language we're looking for to tell us, hey, we're going to do this process. So this time, they give us a percentage, right? They give us a percentage that it's occurring in, okay? And we want to go back to the standard deviation. So standard deviation is kind of like the observation. That would be the beginning of the process, where the proportion is over here. So if you recall, if I'm starting here, starting with the proportion, and I'm working back, where in the calculator do we go? Inverse norm. I do have one little thing to show you though. For this one, it says it exceeds 60 inches in 15% of years. So here at the 60 mark, we're exceeding that 15% of the time. What's the problem with this? We touched on this yesterday. Does the calculator understand greater than? No, it doesn't. So we actually can't use a 0.15. What do we have to use in its place? Exactly. We need to use 0.85. Okay? Because the calculator only understands percentiles. Okay? So you need to know that if you're looking at the greater than and you're trying to inverse norm that, you have to reverse it to put it in the calculator. So what we really need is this 0.85. That's what we're going to be inverse norming. Because again, that's all the inverse norm program knows how to do. It can only do percentiles. So when we type that in, inverse norm, 0.85. Again, ignore all of that. Again, what did we just find? What is that number? Where are we along our little flow chart? Z-score, yeah. Whenever you use inverse norm, it is popping out a Z-score for you, okay? So, (1.04), and again, that is a Z-score. All right, so we're at Z-score. We're still looking to head back to that standard deviation. So again, what's the next step? How do I go from Z back to here? What do I use? Formula. So using the formula, well, I have the Z-score this time. It tells me my observation is 60, right? That's what I'm looking at, with mean of 55, and I want the standard deviation. So again, just to simplify this, so again, how do we handle this when that standard deviation is on the bottom? What do we do to actually finish this calculation? Yeah, multiply this up, and then what do I do with this? Divide it down. All right, so in the calculator, again, trying to keep this as exact as possible for as long as possible. Oh, there it is. If I take 5 divided by that, is that one of our answer choices, hopefully? A. Perfect.
I'm confused. No, okay, so wait, what did I do wrong right here?
Nothing.
Oh.
So now the top would be 5 equals 1.04. So you multiply this up and then divide that down.
Okay, okay.
All right, guys, one more thing. One more thing. So, also you have that piece of the homework you can do now, the second piece of the 2-2 packet. And then because it's a Friday, I'm also going to give you one of these. No, okay, actually, I'm super excited about this one because this is one from the year that I took the AP exam.
No way.
Yeah. So you guys get to see one of the questions I got. But
I wish. I should have 4 GPA. I heard what you guys.
I should definitely deceive myself by telling you when the
Blackjack
solution
game?
figure
I
out
don't
what
mind.
year it's from.
I win, he brings up a spade. Two year old break up a spade. I deal with 20. I flip 13, get 821. He's gotta break up a spade. He's mad. He's mad. The cards never lie. I didn't say anything. You were like, you said a statement and it didn't. Oh, boss. Oh, split him. Split him. Split him. No, it's me. Oh, them. Yeah, so now you gotta break up with your little Asian fetish guy. I thought you ate my breakfast bar and you won't say it. It's just one free time. Actually twice. One. I was hungry. You ate too much? Sorry, depends on what it is. I'm just going to. I really like the chocolate. Them things are unreal. Those were last so lit. I was gonna use it for Saturday morning. That was ridiculous. No, I didn't put that twice or whatever. 2 out of 3 games. That's all you got. 2 out of 3. You're making racks. I'm actually
Hey, can you have this 7 from me?
So wait, what score is that on?
Out of 4. So everybody gets a 5 just for doing it. So last year on the FRQs, national average for every one of them was below 2.
Holy moly. My other one was 1. Don't get his head any bigger. Don't get his head any bigger.
Dev, how did you get a higher score than the
Crapper to me when we did it, when I taught you how to do it. Like, I literally taught him through how to do it.
Dev, he's got so much heart. Isn't that weird? The other crappy, and then you got higher score. He's got so much heart. Who leaves it all out on the field? Who goes for every loose ball on the court? Who does the jellies come off the jellies? Who hasn't played 2K? Who hasn't played 2K19 yet?
Oh, there was someone else. There was someone
Who
else.
hasn't played 2K19 yet? Devin Roberts.
I played Prelude.
My grandma played Prelude.
circle, that's like
Oh,
the
this
page
is the
turn.
bottom. Double
Yeah.
down.
Someone take the 10.
Double down.
We have to talk to them. He drove me home from school or from night school.
17. 16.
Send it. No. Send the 16.
Oh no.
Double down. Double down.
Hey, Max making a good guess. That's in his chat.
Okay, give us up a 19. Love blackjack. We get it. We win 19.
Lost. Lost. Push. Push 2 and lost the rest. Can we actually put some on this hand? I'll put a 20 on this hand. I have 7 black 15s,
Oh,
6.
we both just
I'm winning
did
by 1.
Wait,
They're tracking our team. I'm winning by 1. You get tomorrow. Or someone that's.
they have it
Wow,
really
dude.
low.
I didn't know that was a thing. Yeah, perhaps.
Yeah.
Are you tracking anything else or no?
Okay.
So it's kind of weird, but
That is kind of creepy.
I'm glad you guys know so I'll put it in.
But like a Google Doc on our computer.
They tallied up the amount of time I'll ask for black he's at 7, I'm at 6.
Dude, I thought
Flip them.
you just got like you didn't know we were putting down.
I didn't, I ordered 6.
I mean, you had
16.
you more than 7.
Apparently. Hey, how many days of school do you have?
Two batteries.
You
A
just
lot more
get
than
yourself
7,
out on
right?
the 13. Oh, I just did 60 times that.
Yeah.
That doesn't make sense. You hit 16, 7, you always hit 16. That's what the guy said. Hey, give me half. Oh, yes, we both got
Hey guys, can you make sure too, if you are borrowing one of my calculators, can you make sure I get that back, please?
No, because I can't read it. Okay, I'll play you as the dealer.
No, I just did it when I first started.
Why?
I don't know. I hit my head on it, and I just looked up
I'm
and
gonna hit.
it was a flag.
How much that? 19? 20.
One-on-one is like hard. That's what that one guy kept saying for. He's like, you don't want
Unless you had, unless you had 16 hit every time, 19.
Of course, 16 hit every time. 16 hit every time. Except for that one big construction worker basically bitch at me because I lost the table to him. My butt. You played for yourself.
Look what he said.
I'm saying he's better than almost.
And I'm like, dude, first of all, it's 4 a.m. Shut up.
And he was like,
You lost the table in hand. Dude, I'm not playing for my balls.
oh, he's showing him. He was like, you've been like rushing. I was not going to talk about it. He told me to do something and I was short.
I want my points card getting taken away.
The dealer? No, the construction.
Huge game.
Beyond big.
Bro, tell me that guy just wasn't. Ferb started chirping back at him. Ferb wasn't just a dick. Yeah, Ferb started chirping.
My joggy. I finished that.
Pastor, you stay at the casino long enough, you can get $2 breakfast, and it's the greatest thing in the world.
No, no.
You get to choose pancakes, your choice of sausage or bacon, bread, and then breakfast potatoes.
Okay, that actually sounds really good.
For $2.
That's a really good deal.
It was a wonderful deal, especially at like 3:30 in the morning. No, this was during summer.
Oh, okay.
Don't you worry.
Ants.
I was thinking that sounds really good.
Hard. I'll give you that.
What's up?
Ants.
Running aces
my former students have been joking with me that I need to teach myself to count cards.
Oh yeah. I'll tell you when big money.
Well, and as an athlete, so I could probably actually be really good at it.
Yeah,
Dang,
my
Dev.
mom tells me to go play
I'm
that.
not gonna lie, you look good fly today. It's fresh. Look at you.
Thank you.
I'm just
Hey
impressed.
guys, I'm still missing a yellow calculator. Does somebody have it? Oh, perfect. I was getting nervous. I don't want them wandering off.
Foxy?
Foxy, right? Sure. I'll check shorts. I'll blow it. We can go on after these.
I mean, although you look
That's
fresh,
not
every time you
go.
go, you look pretty fresh.
What?
I'm gonna take it. I'm like embarrassed and feel like I messed up a little because like I know some right away.
Oh.
Why was there?
I was just in a hurry, I think, 'cause I had to work.
Oh yeah. And a lot of people completely forgot to interpret, so they gave me answers and like nothing else. Like, no.
Yeah, I think I definitely did that too. Which also, I've been having to grade, like, I proctor for mail, so like, I've been grading, I grade papers, but doing that one is getting the same stuff, so I did
Definitely. We both do. That's hard.
Got you!
Wait, wait, I feel like a hot mess now.
Yeah, I do that.
Huh.
It was so slow. I had no idea what it was.
Yes, sir. Yeah. No, this weekend is my plan. Is my plan.
Grind it out.
That's my
Get
plan.
it done. I love it.
So I'm hoping to have 4 or 5 pieces of paper.
I would love it.
Okay.
Love it so much.
I would love it too, because then it makes my day more fun.
Guys, can I get some M&M's?
Oh, right. I did promise that. Please tell me that was good. Okay. I knew it was good.
Dogs only. Dogs
Okay,
only.
well, let's be honest. I've seen
Dogs
guys
only,
do
Jay.
weird things.
I will.
You're welcome. Have a great weekend, everybody. I'll see you on Monday / at the games.
For like my grade, it's at like a 92 right now, but like getting that up to an A should be like the hardest thing, right? Especially since we're like so early right now.
Correct.
Okay.
Oh yeah, that's still totally doable. And don't forget, because it's an AP class, naturally it's
Yeah,
going to
it
go
goes
up
up.
anyway.
Well,
So,
that's like why I want to be at an A, so it's like.
oh, because it goes above a 4.0 then.
Uh-huh.
Smart. But no, like it's totally doable still, because we only have one test in the grade book.
Yeah. Okay.
Yeah.
Thanks.
Is there any way I could borrow a calculator for the weekend? Or...
Yes. Let me just write down that you have one, just because otherwise I'll forget, because I have to find a span for the goldfish. But yes.
Okay.
So and then just
Turn it on.
yeah.
Yeah.
And I probably won't even need it before school. Just bring it back during class. Because
Okay.
my second hour shouldn't
Yeah.
need.
Okay.
Shouldn't need that.
Because like yesterday I was like, shoot, I don't have a graphing calculator.
And you
How do I
literally
do
can't
that?
do
Yeah, I
this
was like,
without
I
it.
can't do this without one. Yep.
Yeah. Have a great weekend.
You too.